Okay, back to calculus. So we started to talk about concavity on Monday, and we have a number of homework problems. Any questions before we start? Either about relative maxima, relative minima, critical numbers, extreme points, first derivative test, knowing when a curve is concave up or concave down. So there's the formal definition. A curve or a function graph is concave up on an interval if the derivative, this is the derivative, is increasing on the interval. And we say the curve is concave down on an interval if the derivative of the function is decreasing there. Now, a function is increasing if it's differentiable. The function is differentiable and it's increasing, the derivative is positive. So if the derivative is increasing and the second derivative exists, if the second derivative exists on the interval, then concave up means the second derivative is positive. Concave down means the first derivative is decreasing, so the second derivative is negative, and these are the second derivatives. And where the curve changes from concave up to concave down, or from concave down to concave up. So a point where this happens is called an inflection point. And at an inflection point, if the function is differentiable, the second derivative is changing from either positive to negative or negative to positive, which means it's going to be zero. So at an inflection point, either the second derivative doesn't exist, or if it exists, it must be equal to zero. So this is the basic sort of geometrical concept about concavity or convexity, same thing. And sort of like the typical case is a cubic curve. Cubic curve is a function like y equals ax cubed plus bx squared plus cx plus d. You know, if a quadratic curve, that's just bx squared plus cx plus d. That's a parabola. A cubic curve, if a is positive, the curve always looks like that. And there's always going to be a point with the relative max, and there's a point where there's a relative min. The curve is going to be concave down, from minus infinity up to a certain point, and then the concavity changes, and here it becomes concave up, and right here in the middle, where it changes from concave up to concave down, that's an inflection point. So it's very nice to know the general behavior of a cubic curve, because it encapsulates, like in the purest form, the idea of a part of a curve that's concave down, an inflection point where the concavity changes, and then it becomes concave up. If A were negative instead of positive, the curve would go in the other direction. Instead of up, down, up, it would be down, up, down. But for A positive, that's what the curve looks like. So let me do some problems about concavity, and then I will explain what is called the second derivative test. The first derivative test says on an interval where the first derivative is positive, the curve is increasing. On an interval where the first derivative is negative, the curve is decreasing. So this is in section 4.4. Let's look at number 21. So number 21, we have the function f of x equals x cubed minus 6x squared plus 12x. Actually, let me do this on a clean piece of paper, so because there's a lot of writing to do. Section 4.4, number 21. F of x equals x cubed minus 6x squared plus 12x. So let's look at everything we can about the function. Where is it increasing? Where is it decreasing? Where are there relative maxima and minima? Where is it concave up? Where is it concave down? Where are there inflection points? So let's first compute the first derivative. F prime of x is 3x squared minus 12x plus 12. And the second derivative is 6x minus 12. Let's see, this is 3 times x squared minus 4x plus 3. And we're lucky that this factors nicely. This is 3 times x minus 1, x minus 3. Second derivative is 6 times x minus 2.
Professor?
Yes.
No 4.
Sorry?
No 4. The last 3 that.
Sorry, thank you. Thank you. I just wrote it down wrong. So this makes it x minus 2 squared. 3x squared minus 12x plus 2 factor out 3x squared minus 4x plus 4, 3 times x minus 2 squared. So this only critical number, so forget about this for the moment. So that's the first derivative. What can we say? F prime of x is greater than 0, because it's a square, for x not equal to 2, and f prime of x equals 0 at x equal 2. So this is the only critical number, but the function is increasing everywhere because the first derivative is positive. So f of x is increasing from minus infinity to plus infinity because the derivative is always positive, except at this one point where there's a critical number where it's 0. Okay. So no relative max or min. What is the second derivative? 6x minus 12, or 6 times x minus 2. What can we say about this? This is positive if x is bigger than 2, negative for x less than 2. So f of x is concave up on the interval from 2 to infinity, concave down on the interval from minus infinity to plus 2. And f of 0 is equal to 0. So what can we say about this function? First of all, we know there's an inflection point at x equal 2 because the concavity changes at x equal 2. Let's see, f of 0 happens to be equal to 0. What does f of 2 equal? 2 cubed minus 6 times 2 squared plus 12 times 2. This is 8 minus 24 plus 24, that's 8. So the point 2 comma 8 is an inflection point. This curve is concave down until you get to the inflection point, and then it's concave up, but it's always increasing. So there's one inflection point, curve is increasing everywhere, and concave down, concave up. Okay. Any questions about that? Let's see, that was yeah, go ahead.
Okay. Why? When you how do you find the inflection point?
The inflection points occur where the second derivative is, sorry, the inflection point occurs where the concavity changes from up to down or down to up. So this curve is concave down until you get to x equal 2. And then after that, it's concave up. So where the concavity changes from down to up is an inflection point.
So how did you find the coordinates of that point?
Well, so this tells me the inflection point occurs when x equals 2. This is my function, x cubed minus 6x squared plus 12x. You plug in x equal 2 and calculate it.
Yeah, it's the 2 that I don't get. It's like
so
the 2 is
this is the second derivative.
is the 0 of the function.
No, It's the second derivative. Here's the function. Here's the first derivative. This is the second derivative.
Yeah, how did you find the 2 then? The 2 and the 0?
This is the second derivative. Do you see this?
Yes, I see.
When is this term equal to 0?
X equals 2.
Exactly. When is this positive?
When is positive?
Yes,
Positive when X is bigger than 2.
exactly correct. When is this negative?
It's negative when X is 0.
No, well, it's true, but what is all x for which this is negative?
Less than 0.
No, x less than 2.
Oh, yeah, less than 2.
Okay, so the second derivative goes from negative to positive when x is 2. That means x equal 2 is the x coordinate of the inflection point. And when x equals 2, f of x is equal to 8.
So what about if the second derivative is 0 then?
That's where the second derivative is 0. That's where the inflection point occurs.
No, I mean, if there is no second derivative, like when we took the first derivative to find the second derivative and we find 0, how to solve that?
I don't understand what you're asking. Here's the function.
saying,
Here's the first derivative. Here's the second derivative. And
okay, so let's
you study the second derivative to determine where the function is concave up and where the function is concave down.
let's say if the second derivative is the whole number.
What do you mean the whole number?
Whole number like 6, like yeah.
You mean if the second derivative is 0 at 6?
Yeah, 0 or 6.
That means that you have an inflection point when x is equal to 6.
I'm sorry?
That means you have an inflection point when x equals 6.
So by graphing the function now that we can know if there is a concavity or not?
Well, let me do another problem so maybe it'll become a little clearer.
Okay.
So this is homework problem 19. Here we have the function f of x equals a half x to the 4th plus 2x cubed. So the first derivative is a half times 4x cubed plus 2 times 3x squared. So that's 2x cubed plus 6x squared. Let's see, this is 2x squared times x plus 3. Right? 2x cubed plus 6x squared. If I factor out 2x squared, I get x plus 3. So f prime of x is equal to 0 when x equals 0 or x equals negative 3. So these are the critical numbers for the function. If I just look at on the number line, minus 3 and 0, when x is bigger than 0, f prime of x is positive and the function is increasing. When x is between minus 3 and 3, the derivative is also positive and the function is increasing. When x is less than minus 3, the derivative is negative and the function is decreasing. So let's see, and what is the value of the function at these points? F of 0 is equal to 0. F of minus 3 is a half minus 3 to the 4th plus 2 times minus 3 cubed. This is equal to 81 over 2 minus 2 times 27, which is 54, which is 108 over 2. So it looks like this is minus 27 halves. So if we were looking at this function and just wanted to know where it's increasing, where it's decreasing, and where it has its relative maxima and minima, -3 and 0. So at 0, it's 0. At -3, it takes on this value, minus 27 over 2. The function is decreasing until it gets to -3, and then it's increasing. So we have a relative minimum at x equal -3. The function is decreasing, and then it's increasing. Let's see, actually, just to make this more interesting, if I factor out a half x cubed, this is 2x plus 1. So this is also equal to 0 at x equal minus a half. Is that right? When is this equal to 0? This is a 1/2 x cubed, sorry, times x plus 4. All right. Factor out a half x cubed, I get x plus 4. So this is also equal to 0 at -4. So at -4, this is equal to 0. And then it comes down. You have a minimum of -3, and then it's going up. So that's just looking at where the function is decreasing, where it's increasing, and where it has its relative max or minima. But then we want to look at concavity. So this is the first derivative. What is the second derivative? It's equal to 6x squared plus 12x. Differentiate once, you get 2x cubed, you get 6x squared, you get 6x squared, 12x. So this is 6x times x plus 2. So this equals 0 when x equals 0 and x equals -2. And the second derivative is negative when x is less than -2. And x is less than -2. Sorry. Second derivative is positive when x is less than -2, because negative times negative is positive, and when x is greater than 0. And the second derivative is negative when x is between 0 and 2. Because when x is when x is between -2 and 0, from here to here. So this function is concave down. Oh, sorry, I keep saying the wrong thing. Second derivative is positive for x less than -2. So for x is less than -2, this function is concave up. It's concave down from -2 to 0. And then it's concave up again. So we have the line x equal -2, the line x equals 0. The inflection points when x is -2 and when x is 0. When x is 0, y is 0. When x is -2, if you evaluate the function as -2, this is 8 minus 16, you get -8. So the coordinates of the inflection point are 0, 0, and minus 2, minus 8. Okay. Let me just run through this again, because this is a basic problem. Namely, it's a fundamental problem in Calc 1. If I give you a function, tell me where it's increasing, where it's decreasing, where it has a relative maximum or minimum, where is it concave up, where is it concave down, where does it have inflection points. So we start with this function, a half x to the fourth plus 2x cubed. You actually want to know where it's equal to 0. Let's see, if you factor out a half x cubed, you get a half x cubed times x plus 4. So it's equal to 0 at x equals minus 4. And of course, also at x equals 0. Those are the x-intercepts. The first derivative is 2x cubed plus 6x squared. That's this. The critical numbers where this equals 0 are 0 and minus 3. But if you look at the intervals where it's increasing and decreasing, it's decreasing from minus infinity to minus 3. It's increasing from minus 3 to 0, and then from 0 to infinity. So the function is decreasing, and then it's increasing forever. Then you examine the second derivative. The second derivative is 6x squared plus 12x. That's 6x times x plus 2. That's equal to 0 when x is 0 or minus 2. So those are the only places where you can have an inflection point. And if you look at to see where the second derivative is positive and negative, you see there are 3 intervals. Here it's the second derivative is positive, it's concave up. Here the second derivative is negative, it's concave down. Here the second derivative is positive, it's concave up again. And the graph of the function looks something like that. And since you have the advantage of knowing Maple or some other calculus software, you could actually graph it on your computer and see very clearly what's going on. Any questions about this?
So here there is no relative maximum?
Correct. Let me keep doing these problems because they're really very instructive. So 1921, number 23. So this is the function f of x equals 1/4 x to the fourth minus 2x squared. If I factor out 1/4 x squared, I get x squared minus 8, I think. 1/4 x to the fourth minus 2x squared. So this is equal to 0 when x is 0 or plus or minus the square root of 8, which is plus or minus 2 root 2. So these are the critical numbers. And we look at these on a number line, 0, 2 root 2, minus 2 root 2. A half x squared is always positive or 0. X squared minus 8 is going to be positive if x is either bigger than 2 root 2, the function is positive and increasing, the derivative is positive, the function is increasing, and for x less than minus 2 root 2, the derivative is positive and the function is increasing. For x from minus 2 root 2 to 0 and from 0 to 2 root 2, oops, I'm sorry. I just made a stupid mistake. So I'm going to cross that out and start again. So this is number 23. F of x is a fourth x to the fourth minus 2x squared. If we want the x-intercepts, I just set this equal to 0, but this is 1/4 x squared times x squared minus 8. So this equals 0 when x equals 0 or plus or minus 2 root 2. And these are the x-intercepts. These are the places where the graph crosses the x-axis. The first derivative is x cubed minus 4x. That's x times x squared minus 4. That's x, x minus 2, x plus 2. And this equals 0 when x is equal to 0 or plus or minus 2. So these are the critical numbers. And on the number line, when x is bigger than 2, these are all positive, the function is increasing. When x is between 0 and 2, I have positive, negative, positive. This is negative. The function is decreasing. From minus 2 to 0, this is negative. This is negative. This is positive. Negative times negative is positive. The function is increasing. And when x is less than minus 2, this is positive, but this is negative. The derivative is negative. So the function is decreasing. And because it's interesting to know, what is the value of the function at plus or minus 2? 2 to the fourth, 16 over 4 is 4, minus 8 is minus 4. So when we start to get an idea of what the function looks like, the function is, it has a relative minima or maxima at the points, let's see. So when x is 2, the value of the function is minus 4. When x is 0, it's 0. At minus 2, it also has the value minus 4. Here, the function is decreasing, increasing, decreasing, increasing. It crosses the x-axis at plus or minus 2 root 2. That's a little bit less than 3. So this graph is decreasing, increasing, decreasing, increasing again. Kind of looks like that. So here and here, we have relative minima. Here we have a maximum, a relative maximum. But what about concavity? To understand concavity, we have to look at the second derivative. The second derivative is 3x squared minus 4. That equals 0 when x squared is 4/3 plus or minus the square root of 4/3. And again, if you look at these 2 points on the number line, square root of 4/3 minus the square root of 4/3. When x is bigger than this, here, second derivative is positive, concave up. Similarly, when x is less than minus 4/3, second derivative is positive, concave up. And in this interval, second derivative is negative, so it's concave down. So we have inflection points at x equal plus or minus square root of 4/3. And f of plus or minus the square root of 4/3 is equal to what? Well, when you square the square root of 4/3, you get 4/3. You square it again, you get 16/9 times a fourth minus 2 times 4/3. So that's equal to 4/9 minus 8/3, which is that right? Let's see. 4/9 times a fourth, 16/9 times a fourth is 4/9. 2 times 4/3 is 8/3. This is 24/9. This is minus 20/9. So there are these two inflection points. These are the inflection points. And at plus or minus the square root of 4/3 minus 20/9. Huh. So there is, in fact, quite a lot to do to try to understand the curve using just the first and second derivatives. Okay. Any questions about these? I mean, the next exam could basically have just one or two problems. This is like one problem, but you have to really know a lot to solve it. And not that you have to know a lot so much, but you have to know everything. Okay. So there's just one more thing in this section that we have to do, and then we've covered everything in our lesson. And that is the second derivative test. So this is going to be a short class today because I don't want to get too ahead of the syllabus, and this is exactly as far as we're supposed to go. Remember that at a relative maximum or relative minimum, where you have some function y equals f of x, the derivative is 0. That is, the relative maximum and minima occur at the critical numbers. Numbers where if there's a derivative, the derivative is 0. But how do you tell which is which? If you find a point where the derivative is 0, it could be a relative maximum, it could be a relative minimum, or it could be neither. Right? I mean, you can have a curve that looks like f of x equals x cubed. This is the graph. And f prime of x is 3x squared. So f prime of x equals 0 at x equals 0. but this is not a relative minimum or a relative maximum. So just because the first derivative is 0 does not imply that there must be a relative minimum or maximum. But how can you tell? So let's look at a picture and we'll see exactly what's going on. Suppose you have a relative maximum for y equals f of x. That's what a relative maximum looks like. Here's the relative maximum. As you approach the relative maximum, or in the neighborhood of the relative maximum, this curve, so let's say this is a relative max at the point a comma f of a. Suppose this is a relative max. What is the concavity of this? Where you have a relative maximum, your curve is concave down. Where the curve is concave down on an interval, the second derivative is negative. So if f prime of a equals 0 and the second derivative is negative, you put that together and you can conclude that there's a relative maximum. Okay. So if you're looking for a relative min and max, first you find where the first derivative is 0, and then you calculate the second derivative at those critical numbers. If the second derivative is negative, you know for sure you have a relative maximum. But suppose the curve looks like this. This is the point a comma f of a. And this is a relative minimum. But where you have a relative minimum, the curve is coming down and going up. This curve is concave up. So the first derivative is 0, and the second derivative is positive. That means you have a critical number. The curve is concave up through that point. That means you must have a relative minimum. So if you're looking for the relative max and relative mins of a function, you first find the points where the derivative is 0. And then in each of those points, you evaluate the second derivative. If the second derivative is negative, you have a relative maximum. If the second derivative is positive, you have a relative minimum. Unfortunately, there's a third possibility, which is if the first derivative and the second derivative are 0, then you get no information. You could have a relative minimum, you could have a relative maximum, you could have neither. You just don't get any information. But you put all this together, and this is what is called the second derivative test. If the first derivative is 0 and the second derivative is negative, you have a relative max. If the first derivative is 0 and the second derivative is positive, you have a relative min. Okay. So let me do some homework problems that involve, well, let me do some examples. I'll do an example from the book, and then I'll do 1 or 2 homework problems, and then we'll actually be done for today. So here we have the function f of x equals minus 3x to the 5th plus 5x cubed. We want to find the relative extrema. That means maxima or minima. So what's the first derivative? Minus 15x to the 4th plus 15x squared. So that is minus 15x squared times x squared minus 1. Or minus 15 x squared x minus 1 x plus 1. And that's equal to 0 when x is 0, 1, or minus 1. So we have 3 critical numbers. What is the second derivative? It is minus 60x cubed plus 30x. So that's equal to, let me write it as minus 30x times x squared minus 1. Oops, that's not right. Minus 30x, sorry, 2x squared. Minus 30x times 2x squared minus 1. Okay. So at x equals, let's start with 1. The second derivative at 1 is minus 60 plus 30 is minus 30, which is negative. So at x equal 1, you have a relative maximum. At x equal minus 1, the second derivative is plus 60 minus 30 is plus 30. So x equal minus 1 is the relative minimum. And at x equals 0, the second derivative is 0. So at x equals 0, you get no information from this test. And if you were to graph this, let's see. When x is equal to 1, f of 1 is minus 3 plus 5 is 2. F of minus 1 is 3 minus 5 is minus 2. F of 0 is equal to 0. So this function goes through the point 0, 0, 1, 2, minus 1, minus 2. So here you have a relative minimum. Here the derivative is 0, but it still is increasing. Then you have a relative maximum. Let me come down. So this is the point minus 1, minus 2. This is the point 1, 2. Yeah.
Professor.
Yeah, go ahead.
I think you should talk about like the function is increasing, decreasing, right? And you said it relative maximum and
Well, so what the
when,
problem asks us to find is the relative maxima and minima. So they're going to occur where the derivative is 0, or if you have a relative maximum or minimum, the derivative is going to be 0. There are 3 places where the derivative is 0. 0, 1, and minus 1. When I check the second derivatives, I see that this is a minimum and this is a maximum, and I have no information about this. If I want to know where is the function increasing and decreasing, I can do that. I just draw a number line. These are the critical numbers, minus 1, 0, and 1. Again, the second derivative is minus 15x squared times x squared minus 1. So from minus 1 to 1, x squared minus 1 is negative. Negative times negative is positive. So from minus 1 to plus 1, the function is increasing. And when x is bigger than 1 or less than minus 1, the function is decreasing. So decreasing, increasing, decreasing. If I had to find the concavity, which I was not asked to do in this problem, here it's concave up. Here's their inflection point is concave down. Here's another inflection point is concave up. Here's another inflection point is concave down. But that's more than I'm being asked to do. This point's an inflection point, but it's not a relative minimum or a relative maximum. Let me do one of the homework problems. Again, this is all in section 4.4, number 47. It says, find the relative extrema and use the second derivative test where applicable. So f of x is equal to x cubed minus 3x squared plus 3. So the first derivative is 3x squared minus 6x. That's 3x times x minus 2. So this equals 0 at x equals 0 and 2. So those are the critical numbers. The second derivative is 6x minus 6, or 6 times x minus 1. So the second derivative at 0 is 6 times minus 1, which is negative. So x equals 0 is a relative maximum. All right. Excuse me just one second. I'm sorry. I just need to finish this problem and then we're done for the day. So the function, this is number 47, x cubed minus 3x squared plus 3. This is the first derivative. This is the second derivative. When you evaluate it at the critical number 0, the second derivative is negative, so you have a relative max. The second derivative at 2 is 6 times 1, which is 6, which is positive. So x equal 2 is a relative minimum. So you have for this cubic curve, that's the graph, and this relative maximum is occurring when x equals 0, and this relative minimum is occurring when x equals 2. And of course, here is concave down, inflection point concave up. Are there any questions about this? So I've actually done, I think, most of the homework problems on this section. But these, the 2 or 3 sections we've just done, relative minima, relative maxima, first derivative test, where a curve is concave up, concave down, inflection points, and the second derivative test. This is really, really a central topic in this course. And it definitely occupies a lot of the next exam. And in your, I hope in your math lab, whoever is teaching it and whatever program you're using, you also get to solve these kinds of programs using, these kinds of problems using Maple. It's incredibly efficient and very, very, very nice. Any questions about this before we go? Yes, no, good, bad. Okay, everyone, then that's actually it for today. I actually have a department meeting at 2 o'clock in any case. So I made sure that we covered everything that we needed to cover. And enjoy the beautiful day. We will be back on Monday.
Thank you, Professor.
Thank you all. Bye all.
Have a good day. Bye.
Bye.